Hi everyone and welcome to your 8th embedded system lecture, and this is the start of the RTOS. So RTOS stands for real-time operating systems. Perfect. So this is something that you remember from last year, from both courses CA and OS, and you can notice that we have multiple layers when it comes to computer systems. And we can notice here the hardware layer and then the application layer, and in between we have system software. And one of the system software that we can have in a computer is the operating system. And because we're working in the embedded system domain, well, the operating system is a special one called the real-time operating system. However, it still has the same paradigm of normal operating systems, in the sense of it will be providing services to the upper layers and rendering the lower layer, which is the hardware one, rather transparent when it comes to using the different resources and the application layer. And here you can notice something, and you should know what this frontier here, and you should know what that is. And definitely this is the ISA. So what's so special about real-time operating systems compared to normal operating systems? It's in the keyword real-time. So an operating system is here to guarantee the deadlines, the respect of the deadlines, because it's extremely important in the context of embedded systems, because in the literature we often speak of real-time operating systems, and there are different levels of criticality. So you can have extremely critical real-time embedded systems, also known as hard real-time systems, where not respecting a deadline could cause an extreme catastrophe. So the picture that you need to remember from today's lecture is, without a real-time operating system running, there is no guarantee that deadlines would be respected. This doesn't mean that we cannot respect and enforce deadlines without an operating system. However, operating systems are here, real-time operating systems are here to guarantee the respect of the deadline. Alright, there are many operating RTOS, real-time operating systems out there. The one that I used to use prior to my arrival to Egypt is Micro COS2, and this is an operating system that is widely used in the aeronautical domain because it respects a lot of standards, such as the DO128 that deals with safety. Anyways, the one that we'll be using in this course as an example, and the one that you'll be using in your project as well when it comes to the implementation, is called FreeRTOS, and it's as you can see, as you can guess from the name, it's an open source freeware that is available, that is presented as a library that you can use in order to have the RTOS layer in your system. So because we're done with the hardware part of embedded systems, we're tackling now the system software part that will provide services. So we're gonna see the different API, application programming interfaces, that are used for implementing and having different functionality. Alright, you should know that it is ideally suited for embedded real-time applications. So this is us, this is our course, and especially small microprocessors or microcontrollers, and this suits perfectly the AVR microcontroller family, and notably the Atmega implementation that is in the Arduino platform. of course, because we're talking about embedded systems, so we have different real-time levels. So it is suitable for hard and all the way soft real-time requirements. So you can see that we cover all the spectrum of the criticality levels when it comes to real-time systems. You can see FreeRTOS as a kernel. So you remember, if an operating system is made out of different modules, and the most important module of it is the kernel. So the kernel is there to give us the real-time guarantees. Most importantly, the thing that we learned from the OS course is, although we can have only one CPU, we could have the impression of something. So just a reminder, you can always pause the video in order to reflect upon my questions and then resume in order to check yours against mine. So what is the impression that the OS gives our the users, even though we could be working with only one core CPU? It is definitely the impression of parallelism. And we've seen last year with scheduling mechanisms, also known as algorithms, such as round robin, we can see different processes progressing at the same time from a user point of view in a parallel way. However, the round robin, because we have time slices distributed equally between the different processes, this is what causes the impression of parallelism I was talking about. One thing that you need to note is, in the context of real-time embedded systems and embedded systems in general, we talk about tasks and not processes. Alright, so what are the different functions of an RTOS? You can guess that it comes to task management, and task management is concerned with what exactly? So yeah, definitely the creation of tasks, remember, because a task could be non-existent until we create it, then it goes from the non-existent state to the what state? To the ready state. Perfect. So creation, so creating and deleting tasks. It could deal with the control of task scheduling in the sense of making sure that it kicks out some task that is currently running to give place to another task that needs to run, or to get some information about a task. What kind of information can we get from a task? Something that is relatively important. It could be the name, for instance. But most importantly, it could definitely be the priority of the task, for instance. Alright, task management, creation, etc. But then we have to deal with the selection process. So based on a scheduling algorithm, we need to pick the tasks that need to execute. And finally, of course, as we've seen in the OS last year, that the application tasks are here to deal with directly or indirectly with the hardware. So definitely they're gonna be dealing with resources, especially in the embedded system domain, because remember, the embedded system domain is all about sensing the environment and acting on it. So the sensors and the actuators are hardware resources, hardware devices that we'll be using. Hence, we need to handle the resource management and the allocation of those different things. Can you remember from last year how to deal with the different resources and how to make sure that no two tasks, or back then we used to talk about processes or threads, are trying to access a resource at once? How can we manage the access and make sure that there's some kind of exclusive access or something like that? So definitely using tools such as semaphores or mutexes. Finally, of course, if you remember quite well, something called an interrupt is bound to happen in computer systems, especially in real-time embedded systems. And an interrupt could be anything from a unwanted one, such as an exception, so we have to have some kind of handling of that particular exception, or a programmed one. Can you imagine a programmed one or something that is useful in the context of real-time embedded systems? Yeah, it could be relative to resource allocation. So instead of waiting actively for a resource that is already being used by a different task and just delay the whole system, we can go to sleep and get waken up by an interrupt telling us that the resource is free to be used now. Perfect. Alright, so this is something that you all know, and you can fill in the different transitions and the different bubbles. So we have different states, and you can notice that there's a special, transition here. There's no a bidirectional transition. So go ahead and fill them up. First thing first, non-existent. When we create it, we go to ready. When we're elected, we go to running. If we're kicked out, we go back to ready, or if we're done before getting destroyed. Or if we're waiting on something or something happens and we're blocked, we're gonna go to the waiting state, or we can be forced to go to the waiting state before getting a signal that whatever we were waiting for is ready now. So we go back to the ready state, and then to go back to the running state and finish up whatever we were doing. All right. There's no transition here. How come? So of course we don't have a direct transition, because while we're waiting, we could have another task running, so we cannot just go back to the running state. We need to go to the ready state to check our priority, if it's our time to run, etc., etc. Alright, so creation, election, preemption, destruction, event or IO, waiting on a resource, or something is forcing us to go to the waiting, and something is waking us up, telling us you can go back to ready. Now the question is, knowing what you know about real-time embedded systems for now, so what do you think the states that a task alternate between are which ones? So you have noticed that in our real-time embedded systems that most of the programs are made out of an infinite loop, a perpetual loop. So what would happen is, whenever I get to the running state, I will always have something to execute until I get blocked or preempted, right? I will never finish. So I'll keep on running, right? And I will alternate between the ready and the running state. So if it's my turn, I'm gonna run. If I'm kicked out for a higher priority task, I'll go to the ready state, waiting for my turn to go back here. So we alternate between those two. And sometimes this one when we're waiting for something, all right? But basically it's between those two because of the perpetual loop. Alright, so let's see here. If I give you this particular schematic and the quiz, so what can you tell me about it? So apparently we are trying to create two tasks. So the question is, how do we do that in FreeRTOS? Just a remark, whatever I'm teaching you, whatever I'm trying to teach you here, I'm using FreeRTOS as an example, but this is applicable to any real-time operating system out there. However, what would change is the syntax, some semantics. However, the whole idea, the whole paradigm is always the same, all right? Because I've never used FreeRTOS before getting here. So last year I used to use MicroCOS2. However, I have noticed that it is the exact principles, albeit we have some extreme small syntax changes. Alright, so let's get to that. How to create tasks? Well, there's a function that is called a system function that is called a task create, and you can notice that it has some attributes here, some parameters. Alright, and we're gonna dive into the details of the different parameters. But if you're almost engineers now, and you're gonna try and decipher the different things here. So we can notice that we have something called a task code or something like that, or task function, right? So it should be related to maybe the codes of the function itself, of the task. So a task is a process in the context of real-time embedded systems. And if you remember quite well what is a process, this is what we tackled last year. We said that a process is a program, right? It's a code. However, it's not a passive code. It's a process that is wanting to execute, that is currently executing or wanting to execute, that is present in the system, that the OS is aware of. It's not just an idle code sitting somewhere in the secondary memory. So the idea is we need to associate a task, right, to some code. So we need to know that code. So this is the first attribute, most probably. Apparently here we have something, a name, a char pointer here. So basically this could be a string. Okay, so this should give us an idea about something. Okay, something that I recognize called the stack. This should ring a bell. So a stack is a memory space that I use for something. Oh yes, for functions, correct. And something called parameters. Oh, something extremely important. Apparently it's a priority. So priority, because I'm in the context of real-time embedded systems, so sure, some tasks should have higher priorities than others. For instance, if I'm having a system where I have only one CPU executing a task handling the radio, and another one handling the brakes of a car, let's say, so of course the brakes should have the higher priority. And there's something, a last parameter here. We're gonna check those out. Alright, so the question is, if I'm calling this system call, I'm calling this function here, right? So what would be the possible outcomes? Because I believe that you've done a lot of software engineering, especially in Java. So yeah, something should be a return. So it could be either I've succeeded into the creation of the task, the operating system did succeed, or it did not. Make sense? Right. So it's either I succeeded into doing that, and this is the message that you get, this is the return value, or it did not, it failed. It's either this or that. Now the question is, and this is the challenging question that there's a good example of what you could be having in your exams or later in life, in your professional life, is what would cause the failure of the creation of a task. So think embedded systems hardware wise. Alright, so remember, hardware wise, in the microcontroller we have some memories, some program memories, and some data memory, also known as a RAM. So a possible cause for not able to create a task is we don't have sufficient memory for it. Because remember, we have to create a stack for the task. If we don't have enough space for that stack inside our memory, maybe there are too many stacks already created in the system, so this could cause a failure of the creation of the task. Alright, and the exact return message that you could get back is the required memory could not be allocated. Alright, so now I want to check something out. I want to see the different descriptions of the different parameters. So this one, as I said, it feels like it's about the code, so it's a pointer, it's a reference to the function that implements the task, because remember, a task is something created that the OS is aware of. The function is just a piece of code that is sitting somewhere in your hard memory or in your secondary memory. So we need to associate a task, a created task, to the function that implements the behavior of the task. Next, PC name, char, constant. So this feels like a string. So this is a debug name for humans. So we will be able to read the name of this task. Third, it is the stack size, and the stack size could be in either bytes or bits or something else. And in the case of RTOS, it is that something else. We will know what is that something else in the upcoming slides. So this is a number that represents the stack size. We're gonna see what unit is that. Alright, fourth parameters for now, I want you to set it to null, not to think about it. Most importantly, I want you to think about the fifth, which is the priority. So in RTOS, the priority, they go from 0 to some number that should be defined somewhere. Can anyone guess where do we usually define those config constants or macros? In a .h in the header file, correct? And this is, why is it something that is flexible that we can change? Because remember, the RTOS is meant to run on different hardware, so different microprocessors, microcontrollers, etc. So we need to adapt to the hardware platform that we're running on. So what's sometimes possible using a microprocessor is not necessarily big enough to fit in a microcontroller. Hence, the number of priorities could not be the same in a microprocessor or in a compared to a microcontroller. Alright, in the case of RTOS, 0 is the lowest priority, and then we can go to the highest priority that is defined by that. In other RTOS and other RTOSes, so in other real-time operating systems, sometimes it's the other way around. So a low number means a high priority. So it really depends on the operating system. But in free RTOS, it's this way. And the last parameter here, I don't want you to think about it for now. We're gonna see it later. All right. So systematically, whenever you're dealing with an operating system, whether it's free RTOS or something else, you should remember those things. Of course, we need a function that describes the behavior that implements the task. Of course, we need some kind of name to know what we're talking about. Definitely a stack size. We cannot have a function or a task without a stack, without some memory to deal with. This is the office. This is the office desk of a function. So it's workspace. And for sure, we need the priority in the context of real-time embedded systems. For sure. Right? So whether you read this particular one or you use another one, I don't know, someone got into SpaceX and they're asking them to implement a task in a weird operating system called, I don't know, space operating system or something like that, which is the real-time operating system. You systematically think about those 4 parameters: code, name, memory size, priority. Alright, so let's see an example. So here I'm trying to implement a function, right, called task1. I'm gonna see the body of that function. So apparently I'm having some kind of string here, right? So it's a pointer to a character. So it's a pointer to the beginning of a series of characters. And this is the characters that I'm trying, and I'm apparently, I don't really care about it. Apparently I'm creating a variable here of an integer, a special type of integer. I don't care about the rest for now. And not surprisingly at all, from now on we have an infinite loop, right? Because again, we're in the context of embedded systems. And apparently what I'm doing here is, all I'm doing is I'm calling some print string function and printing whatever I had here, and that's it. I'm gonna introduce some delay using a for loop, using that particular thing that I've created here, right? So I'm gonna spend some time here, and that's it. So apparently the behavior of my task will be print a name, get busy for a little bit, and then go back and print the name over and over and over again. Fair enough? Alright, so let's define a second task. As good engineers as you are, you know, in order to create a second task that looks exactly like the first one, all you have to do is copy this one, paste it, and make the necessary changes. But sometimes, because we're good engineers, we always forget, most of the time, we forget to make the changes, and then we're surprised at the execution. Anyways, so we're gonna copy and change some things. So what are the things that we're gonna change here? So most probably the name, and most probably the message I'm going to print, and this is exactly it. So copy paste, changing the name and the message. Fair enough? We're good. Are we good? Can we run the tasks now? 3, 2, 1. Answer is no. How come? Because we've defined the tasks, however we did not create them. Correct. So this is our next step. Let's create them. So usually we do the creation in the main function, usually, and not always. Alright, so let's go for that. So what was the function that we called, the system function that we called? Yes, task create. So x task create, the name of the function. So this is the reference, this is where the code is implemented. The human name, this for me. Whoops, what is that? Yes, the size of the task. Set it for null, set it for null, I don't care about those. And this is the priority. Perfect. So apparently priority of 1, this is so close to 0, so apparently it's a very low priority. Apparently we need to compare it to different other priorities. Fair enough. This is what we did. 10,000, this is a weird number. So using this particular number, can you guess the unit of the stack size? So is it 10,000 bits, 10,000 bytes? Alright, knowing me, if it were bytes that we were talking about, I would have put here 1024 instead of 10,000. But I used 10,000, how come? 3, 2, 1. This is the size in words. So the word is the length, is the width of the memory. And at mega, the size of a word is how much for the data? It's 8 bits, it's 1 byte. Perfect. In MIPS, it's 32 bits. Okay, so let's do that. Let's create the second task. Copy, paste, change what? Yes, I'm gonna change those two. Same Z's, same size. Whoops, same priority. Hold on. So I am having two different tasks with the same priority. My system would go crazy, would it? Let's think for a second. 2 tasks with the same priority, what would happen? Oh, alright, so this could be a round robin scheme here. So this one will go a little bit, that one will go a little bit, and we're gonna alternate between the, and it is the case of the FreeRTOS. Last thing, created tasks, however I need to, so both of them are ready now. Now I need to start the selection process or the election process, and this is done by starting the scheduler. So before that, I'm just in the ready state. Here, some task could go to the running state, the elected, the lucky one. And this is the end of my main. Usually I never reach this part, because when I start the schedule, I'm gonna go to my task. I never get. If I get here, this means that I did not succeed in creating the tasks. Alright, so if you recognize the logo here, this is something that you use apparently in your database or something like that. Bref, it's not the issue. The outcome of the execution, and anyways, you're gonna use Visual in your Visual Studio in your one of your tutorials with me, in order to see a little bit what happens. So what you see here is, yes, definitely, we're checking the execution of the program that we created. So once we've started the scheduler, apparently my first task went first. Okay, so in case of equal priorities, apparently the first one I created will go first, maybe. Second task, third task, second task. Alright, so apparently it really looks like a round robin. So we're sharing time slices between the different created tasks with the same priority. Okay, fair enough. In order to make sure that it is the first created task that is always the first one executed when we have equal priorities, we need to have different scenarios and to compare. Alright, but a hint, most probably it is the case. The first one to be created is the first one to execute. In case of equal priorities, of course. Alright, time. Time is money. Most importantly, times in terms of real-time operating systems, especially real-time operating systems, and it's not special for the FreeRTOS, it's for all real-time operating system. Times is always in terms of ticks, T-I-C-K-S, so ticks. All right, this is why As human beings, we know time by hours, minutes, seconds, milliseconds, nanoseconds, whatever. However, the operating system understands only ticks, and you have a system function that will convert milliseconds that we understand into ticks, so the OS can understand. Fair enough. So whenever you're gonna do something with time inside the body of your task, you need to specify it in ticks. However, you're gonna specify it in ms, in milliseconds, and you're gonna use this function to translate it to ticks so the OS can understand it. All right. Duck, duck, duck. So this is an example, and apparently what I'm doing here is translating 200 milliseconds into ticks and put it in a variable called time in ticks. Well, that's extremely clear. All right, so ticks. Have you ever wondered how the whole system understands the whole concept of time, rising edges, falling edges? Yeah, so each and every time you have something going on, right, there is a generated interrupt. So each tick, your time unit when it comes to the OS, and especially the real-time operating systems, is in ticks. And each time I have a tick, I need to make some decision. Fair enough? So a systematic tick interrupt is happening on each and every tick, whatever your tick is. Your tick is defined in terms of what, by the way? This is CA. Yeah, it's in terms of frequency and cycle time, generally speaking. Yes, definitely. So cycles per instruction and frequency. Fair enough. So let's see this particular scenario. So apparently I have my two tasks, right? And for some reason task 1 went first, and then upon the tick interrupt, this means that someone needs to take over in order to do some context switching, and that someone is no one other than the kernel. And what module exactly in the kernel? The scheduler. Perfect. And then we'll have it for a little bit of time to make a decision whether to continue with that task or to go for the other one, and etc, etc. So in case of two tasks having the same priority, you can notice that we're executing, then time's up, my time slice is up, kernel takes over to give the CPU to the task number 2, then kernel takes over, etc, etc. Fair enough? In terms of ticks, of course. So a tick interrupt is a periodic interrupt systematically, and the scheduler at each tick will go and check things out. Alright, so now that we are aware of ticks, and the kernel speaks in terms of ticks in order to know how to, or whether to switch or not between two different tasks, I need to understand what really happened when I was using the for loop as a delay mechanism in the previously implemented tasks. So if we check this out, so task 1 got to execute, print the message, and then spend some time waiting actively. So it never left the running state until its time slice is up, thanks to the tick interrupt that we have here, and the kernel decided to preempt it in order to give the processor, right, to the second task. And here we can see it with the laser pointer. So my task is executing, printing a message, waiting actively in the for loop, and then time's up, let's kick it out. Times now for the second task, same thing, print the message, wait actively, my time slice is up, context switch, first message. I'm not happy with this for delay. How come? Well, basically I'm waiting actively inside the CPU, so in the running state. This means that if there were any other task with a lower priority, this means that this task will never get to the running state because I'm still there. So I need to do it in a smarter way. This happened, of course, the round robin scheme that we have here, because we have same priorities, and upon the tick interrupt here, I know that my time slice is up and I need to alternate between the two. Alright, and whenever I'm executing, task number 2 will be in what state? Ready, because of the infinite loop, and vice versa. Wherever task 2 is executing, the first one went to the ready state, waiting on its turn. Again, this means that my CPU is always busy with those two tasks, and if there were a lower priority task than those two, this means that it will never get to the running state, because there's always someone with a higher priority inside the running state. Alright, so this is what we're saying. Whenever someone is running, the other one keeps on ready, and when that one keeps in ready, and whenever that one is going to alternate, go to the running state, that one will go to the ready state, etc., etc. The smarter way to do it is to force the running state to wait in the waiting state, and hence clear the running state. So this is forced using a special function that is, if it's a system function, and it's in the name, it's the wait. So here we can notice that the first task got created, right? So it's in the ready, got elected, it's in the running. So the second task was actually created, so in the ready as well. And instead of having this one timing up using the round robin mechanism, I'm gonna force it to wait. So let's find out how we do that in FreeRTOS. And this is the proper way to have a delay, by the way. Alright, so the function call that we're using here is task delay, and of course, because the operating system understands ticks, so we need to we need to have the time representation in ticks. And if we do not have the ticks, all we have to do is use the other function that helps us translate from milliseconds or seconds, it's milliseconds, to ticks. Alright, so how many tick interrupts should I be blocked before getting back to the ready state? So this is the time I'm spending in the waiting state. Alright, let's see an example. So this is my task, the way I created it earlier, and you can notice that the active delay that I created here, I want to substitute it with the passive delay, meaning that I don't want to wait actively inside the running state. I want to go ahead and wait in the waiting state, in the blocked state. So how do I do that? Try and do it yourself. Right, same, whoops. Alright, so first thing to do is, if I wanted it to wait, let's say 200 milliseconds, so I need to call the function that will translate 200 milliseconds into ticks, and I will have my delay in ticks now. And then all I have to do is call the delay function with the number of ticks that I got from the translation. Alright, so the actual 200 milliseconds in ticks are a parameter now for my task delay function. This means that task number 1 will go ahead and sleep inside the waiting state and free the running state for 200 milliseconds. Go ahead and do it for the second task. Take your time. Same thing, different names. Alright, so let's see what happened now. What happens is I'm creating my functions, creating my tasks, sorry. And what difference do you see with the previous creation that I made earlier? So same thing, whoops, the priority is different now. This means that which one has the higher priority? Definitely task number 2. Remember, closer to 0, the lower the priority. In this case, in the FreeRTOS case. Then I'm kicking off the scheduler and we will see what happens. Alright, so you can notice that, yes indeed, second task started because it has the highest priority. However, what? A lower priority task got to execute? Yes, sure, because remember, even though it is a while loop, I am forcing it using the delay into the waiting state. Hence, I'm freeing the running state for the first task to execute. And this one will go ahead once it reaches the delay instruction, will go to the waiting state, and then that one would get awake and execute, etc., etc. So we can see that we're alternating thanks to the delay. But what's really happening there? I want to see the traceability of it, the axis. Let's find out. Alright, so we can notice the two tasks. We can notice that task number 2 started executing because it is the one that has been elected upon the tick. Right? It started executing, and then what happened to it here? Here you can notice that that one went to sleep. Alright? So this made it possible for my task to execute. So here of course I'm not seeing the context switching, but there is a tick happening. Fair enough. And my task number 1 is executing for a short period of time. It reaches the delay function and it goes to sleep. Whoops, this one is not awake yet. The 250 milliseconds are not done yet. What's happening? Alright, so apparently there is a third task that I did not personally create, is executing all the time that neither of those two tasks is awake yet. So what you need to know by now is, systematically, whenever you start the scheduler, the operating system is creating an idle task. Question: what would be the priority of this idle task? Answer: definitely 0. It is the lowest possible priority. How come? Because we don't want it interfering with any of the user tasks that you're creating. Second question about the idle task. Well, if it's the lowest priority ever, can I use it for something? Can I change the code, its body, to do something? Definitely yes. As engineers, we always answer yes. We answer yes, and then we say but, right? So yes, we can. However, or but, we need to understand what to do inside it. What can we do inside it? So here, typically, if you take a second to think about it, anything related to stats, something that you need to log, that is not really important, you can do it while the idle task is executing, because it's wasted time anyways. So you can do some background job. Fair enough? Let's go back to our example. So here, this one is waiting, this one is waiting. I have some free time, my idle task is executing. Whoops, the waiting time is over for my task number 2. It will execute. It will preempt the idle task, because naturally any task that you'll be creating will have a higher priority than the idle one. So I'm back to executing, and then I'm going back to sleep because I reached my delay function again. Remember, it's a perpetual loop. Context switching, same thing, and then back to idle side. And this schematic will go over and over again. Fair enough?